Hi everyone, nice to meet you. My name is Yuxi Hong. So I'm currently a postdoc at the Berkeley lab. It's very nice to meet you, and I'm very honored to be invited by Helen to give a guest lecture at CSE 60 to 30. Okay, so excuse me, I had a bad cold these days, so my voice may sound weird. But today's topic is exploiting data sparsity in scientific applications. Mainly, I will go through my work and my PhD. Okay, so the length will be around 60 minutes. This is a video recording, and I will be online for Q&A after this video. Thank you. The topic is data sparsity in scientific application. So I'm doing HPC, so I'm doing the we are working with MPI and OpenMP and the GPU stuff. But the on top level, so the algorithm level, it's called the data sparsity. So what is data sparsity and why it can be used in scientific applications? I think I hope I can answer these questions during my talk. So a little background of me from China, and I graduated from Tsinghua University. My PhD is in Calst. My advisor is David Keys. These are my research interests: numerical linear algebra, Taylor rank, algorithm design, and GPU computing. I'll explain later what this means. So I will introduce two applications here. The first is adaptive optics system for ground-based telescope, and the second is seismic redatuming by inversion. And for algorithm, I'll introduce the stochastic Levenberg-Mark method, discrete time algebra Riccati equation, and Taylor rank matrix vector multiplication, and the sum of variants. So on the software level, I developed the ships in the air, TRMVM and TRMDC. Once we are talking about the HPC, we should also pay attention to the architecture. So I played with many architecture, like almost all the mainstream vendor machine in the market. Okay, so um, these are the algorithmic solution for HPC application, because currently the simulation data and the experimental data is very large. So, but luckily we can find some common some feature in this data. So, for example, currently machine learning, deep learning is very popular, and the stochastic gradient descent use this select a part of the sample instead of using the full batch, and you can achieve a better time to solution, and also increase the performance of the algorithm itself. So it approximates the gradient and the Hessian, and uses subsampling method to reduce per iteration cost. Also for the algebra compression, which means that if I have a matrix, and is it possible to use some matrix decomposition method like SVD, rank revealing QR algorithm, to approximate the original matrix? We call it a data matrix, because if you typically, if you see some data matrix, if you do the SVD on the data matrix, you can find a feature called the exponential decay, and that is the singular value of the data matrix. Actually, it's exponential decay, and you can use like 20% of the data to achieve more than 90% of image quality. So by reducing this data, and then we can tune the accuracy of the application, and to reduce our data size. Secondly, the third is linear algebra runtime system. This is some advanced software technique. It hiding the data movement by, we call it asynchronous execution in runtime system. This is because the communication takes too much time, and we can by you can use some stress in the hardware to follow the communication while keeping local computation running. But also the mixed precision computation in runtime system. The mixed precision is happen in a GPU system mostly. Yeah. So this is some new hardware feature. High bandwidth memory technology. It's very popular because almost all the accelerators has this high bandwidth memory. We can reach around 1 terabytes per second or 3 terabytes per second on the latest NVIDIA Hop GPU. I think on the there will be more here because the latest architecture is Blackwell, right? Okay, the huge last level cache. So for AMD EPYC processors, it has crazy last level cache, L3 cache we call it. It has 256 megabytes in ROM and Milan, and latest Genoa, it has 700 megabytes. Okay, so also I introduced the later lower precision or multi-precision. NVIDIA found that using the less bits to represent a floating number can reduce the data size and increase the computation. And also in recent research, there's some trend of the customized accelerator that use the SRAM for AI accelerators. But is it possible that we can use these AI accelerators to deploy the scientific application? This is also emerging research. Okay, so let's first look at the AO for ground-based telescope adaptive optics and stochastic Levenberg mark method. So I'm gonna first introduce this atmosphere turbulence. This is, you see, this sum is not perfect circle when we look through the atmosphere. This is because mostly, so you can see the edge of the sun. It is not perfect. It is some. This is because the atmosphere turbulence, and it does not seems to be a problem if we look at this image, but it is a problem when we use a telescope to look at the stars, to look at the stars that is far from us. So this is an explanation that incoming planned wavefront, and this is Earth's atmosphere. You can see there are many turbulence eddies, we call it, in the different layers of the Earth's atmosphere. And then the sun, the planned light wave become the corrugated wavefront. So what AO system is doing is to reduce this effect. So this is how AO systems working when the planned wave light coming from here, and this is distorted waveform. We call it distorted waveform. And then there's a deformable mirror here that can change its shape. And then here is the closed loop. Here is a closed loop, and waveform. If the distorted waveform is detected through this blue light wave, and it will go through a control system. In this control system, finally, it will send some commands to change the shape of the deformable mirror. And then if you change the shape of the deformable mirror, then we can correctly, then we will reduce this distorted phenomenon. So AO system is this control system. It has two parts. The first is software real-time controller, and the second is hard real-time controller. So you can see this waveform sensor is here, and it sent the measurement data into the system. And then the system will average this waveform sensor data to get the current. So this covariance data is actually the current atmosphere, how atmosphere is, what's the turbulence eddy, the wind velocity, something like that. And the software real-time controller, you can think of it as a learning tools that it can learn the covariance and then generate the control matrices. Okay, so once it generates the control matrices, it sends it to the hot real-time controller, and then for any measurement that comes later, it will send the commands to the deformer mirror here, DMM. Typically, the software real-time controller works at 0.1 hertz. This is very slow. However, for the hard real-time controller, it works at around 1000 hertz. It is a real-time system. Okay, so then we have a close look at the software real-time controller, how to build the model. So we can split the turbulence eddy by several layers. So then we want to learn the turbulence eddies, and we have some parameters. So first, we split into several layers, and we think that for each layer, these turbulence eddy are the same. And for each layers, we set some parameters such as turbulence strength, bidimensional wind velocity. Yeah. So this is the input matrix, covariance matrix is like. So each data is you can think of each data, each element in this matrix is a data sample, and you can have. Luckily, we can also get an expression of the covariance matrix, which means that you can use some parameters, layers, turbulence stress, bidimensional wind velocity, to express the elements in this matrix. So then it is, if you have the data and if you have the parameters and the model, then you want to learn the parameters. It's become a supervised machine learning problem. So then this is the analytical, our physical expression, and this is our incoming covariance model data. Then we just do, we want to minimize the difference of them. So so this is the origin, the fx. This is the problem we want to minimize the vector, and this is the objective function. So if we use the SVD, then we can use some SGD first order method to optimize it. So I will skip this detailed explanation. But what the astronomer did in the past, they used a method called the Leeuwenhoek-Mark method. I think they tried to use the SGD method, and they think that first order is not that good, so that we use LM. So that they use LM method. However, what we found is that there is data sparsity in the matrix, and we try to use a subsampling method to solve the problem. This is because the distance, so the value, the covariance, the matrix element in this matrix is nothing but the distance. It is decided by the distance of the two waveform sensor. So like if you this 5 waveform sensor and this 3 waveform sensor, the distance is the Cartesian distance. And then the 6 and the 4, the distance is the same. So it can be, so if the data is the same, then there is a lot of redundant computation inside this. So what should we do? Like SGD, we can subsampling some data point for the computation. So this is the SRM algorithm with fixed regularization. I won't go through the detail. It's just the most time-consuming part of the original Levenberg method is compute the Jacobian and stochastic gradient. It's like the most idea is that we are not using the original, the full batch of the data. We just sample several data point and generate this Jacobian vector in the stochastic gradient. This is roughly the idea. So here is some theory. I won't go into the detail. It just to tell you, okay, you are doing the right thing. But yeah, it's just a theory. It's like we recovered the classic complexity bound for the SGD, and its variant. And here, above the algorithm part. Now we go to the implementation part. So original LM method, it used the GPU. Now we need to redesign the GPU kernel because we subsample the data. So it is stochastic Hessian gradient kernel. We redesign it, and we use block random index because what does it mean? Because if we randomly select the index, then we will have irregular memory access issues. So because GPU doesn't, it's like you will fetch, you are less efficient because you only fetch one data point. And then if it is a float, then you might not get expected the great performance if you compare to if you use the 128 bits load and store. So what we did is that we try to block the matrix, and we select the continuous part of the matrix. Then to make sure the data is accessed in a better way. And then here is the reduction optimization. We just rely on the cube library to perform block level reduction. Okay, so now here we are showing some performance improvement. We break down our optimization strategy, block random index, block reduction. We, from original implementation of stochastic Hessian gradient kernel, using the block random, we increase 3.6 and then 1.2. And there is some acceleration. And then we are showing the time breakdown of the first iteration. So the data DF is called the data fraction. It's just like the batch size, but it's just the 0.1 times the full batch is the batch size. Yeah, you can see most of the time is spending in the stochastic Hessian gradient kernel, and then we also do the multi GPU implementation, where finally, but most of time is spending on the Hessian gradient kernel. And also we do the experiment on the 3 generation. So this is usually how we benchmark our algorithm. We need to make sure that this algorithm runs well on at least several generations of the GPU, and break down the algorithm and check which part is the most time consuming part, and also when we do scaling, and we want to make sure it scales well. So then this is the end-to-end simulation of SRM with different data fraction. It just tells you when I change the data fraction, which the threshold ratio. Okay, so it's just it's like it's like the clocks and the image classification rate, correction rate. But here is we use a threshold ratio to tells you how much uh, how does our AO system behave. So the higher the better, and you can, and also 1% difference is significant, and we just brute force choose all the data fraction and find okay 1.1 minus 3 is best. That's it. Okay, so this is numerical result compared to the serial convergency. So here now we are looking at the not the kernel, but looking at the whole SRM. When we plug in our SRM to the plugging our kernel to the SRM, and then what will happen? And this is the normalized gradient square. Um, so this yellow line is the expected convergence rate, and you can see that our experiment is below this convergence rate, so we are good. We also compared with other first order state of the art optimizer, and you can see that indeed our SRM behaved the best among them, and yeah, and here these are just the setting of the experiment. Okay. Mm, yeah. So here we accelerate the software real-time controller of the AO system by we first have a new algorithm called the SRM algorithm. And then we present the theory of the SRM with the fixed regularization. And this is the algorithm part. And for the implementation part, we have some new GPU kernels to implement to help implement. And on top of that, we do some optimization of the kernel. Yeah, and for the benchmarking, we compared with other first order and original method and to prove the superiority of our algorithm. Okay, so next is there we call the discrete algebraic Riccati equation in software real-time controller. So actually, it is LQG is control is from a control theory, but usually we collaborate with the application expert, and here actually I don't know this formula very well, but to be honest, but someone in our team may know it very well, and then he he said, okay, so this is what we used, and we need to do it fast, and do have some, and we have some threshold that you can utilize. Do you have some whatever you can do GPU, you can do CPU, but I need to do it fast. So this is, and then after I will take care of the computation and try to lower the precision, try to do the rank, do the SVD, to try to explore the data sparsity in this, try to and play with these things. So basically, this D is mm, yeah. So actually, this is another way. So predictive controller is another way to do the SRTC, and it has better closed loop performance. So the threshold ratio can be larger than 40% for large dimension. Previously, we can do only 25%. And but here, this computation formula here is very large, and it's very time consuming to finish. So D is spatial. Here, I won't go into the detail of these parameters, but here are some feature of this formula. First, it has very rich matrix operation, which means gem and the gem and the triangular solver, something like that. and it represents a good candidate for the GPU hardware because it is very rich in level 3 plus. Okay, so this is the block algorithm. Basically, we instead of we doing the instead of processing the matrix row by row, column by column, and we process it using using a block by block. So to do block by block is to increase the data locality um, or data reuse on the on different architecture from because the computer prefer this because computer prefer so we rely here is some implementation optimization detail. We are using computer. Here's our implementation optimization detail. We rely on Chameleon library, which is advanced runtime system, linear algebra runtime system. We rely on the CUDA and the MKL plus, and so here we didn't change the algorithm this time. We just tune with the execution, tune with the multiple GPU, overlap the computation and the communication. So you see, for example, asynchronous kernel execution, multi-threaded blast on CPU, because you have in the CPU you have blast and the GPU you have the jam, but um, it can relieve the GPU likes large time. So this is the computation DAG of the DARE. It's a single iteration, and so this is the synchronized one, and you can see this is the single asynchronous iteration. By doing asynchronous execution, we can stack this critical path of the computation. This will have some benefit to increase the performance of the program. And this is the 5 asynchronous iteration. Yeah, so we also do the performance breakdown, and we benchmark with Intel CPU A100 and different technique that we optimization technique that we use. So we are 6 times better than the CPU, and we just processing the large memories, large data size dimension by 7 minutes. The peak of the A100 is 20 teraflops, and now we can reach around 13 teraflops after we use all the optimization. So this is the scalability result. And we scale it to from 1 A100 to 4 A100. You can see we can have a decent scalability for the large number of the data size. Okay, so in this part, we accelerating the software real-time controller by using a design a high performance data implementation. We didn't change the algorithm. We just bring the algorithm and using the asynchronous iteration, some optimization technique on the GPU and to improve the performance. So here is the TRVM in hard real-time controllers. And let's after look at the SRTC, let's look at the hard real-time controller. So the input is the SRTC's output, the controls matrices, and also the waveform sensor data is streaming data into the system. It's like the computation are a series of dense matrix vector multiplication. It's like the control matrix is a gigantic matrix, but the waveform sensor data is a vector that stream into the system. But you need to do this dense matrix vector multiplication very fast because the HRTC works at a very high level, 1 kilohertz. So the compute pipeline latency should be below 1 milliseconds. And also, the stable time to solution is very critical to ensure the stable operation because it is a real-time system. And if there is some delay in the first round, this delay will be increased little by little as the iteration goes. Okay, so this is the key hardware component called the deform mirror because, like I said in before, it can change the shape and change the light wave. But the physical accuracy of this deformed mirror is very limited. So which means that it can only accept the maybe 4 digits input. So it is not useful if you have 16 digit or 8 digit result. You just need a 4 digit result. So it gives us some potential opportunity to do the approximation computing. So this is the project team that we are work with. It's these are just introduction. So here is you can see the control matrices. So we are, and it's a short and wide matrix, and we use this short and wide matrix to time with a vector. So here the length of the rows is around 5K and the columns is around 20K, and it's a dense matrix. You can see it's a lot of structure inside, and they are connected to the system parameters. So we truncate, we split the matrix into block or tile. And then we do the SVD on each tile. And then we choose the certain accuracy to say, okay, the norm of this tile should be small to, for example, I select 10 a singular value. And I compute the approximated matrix and I compare it with the, for example, the original tile. And then I say the difference should be smaller than 1% or 10%. So this is the accuracy means. So tile size is 298. So you can see, and the color is the rank. So the black is the lower rank, yellow is the higher rank. You can see there's a lot of low rank feature in this data matrix. And then we do a statistic analysis on the flops that we are doing if we really use the U and V basis, or if we use the original tile. So this red dash line below this, the rank below this line, which means that you will have computation, theoretical computation reduction when you use the U and V matrix for the computation. Okay, so then we think, okay, let's do the low rank, and every tile is a low rank U and V vector. So how to leverage the data sparsity? We first compress each tile into U and V basis. Here is the 4x6 tile, and blue is the U basis, and the V is the green one is the V basis. And then, but after we doing this, then you might thinking, let's just do the, we can also split the X into several times. Yes, it is correct. But first thing we do is stack the U and the V bases. We stack it because that during the computation, the green column, so the UV basis on the same column, it will use the same block of X. Then instead of we doing the NVM multiple times, we can just launch one NVM for this block, for this column stack the V basis. Yeah, so this is what we did. So we first stack them and multiply the V, stack the V basis with the X, the tile, one of the tile of the X. And then we got the YV vector, the intermediate result. So this is not the final, so we need to shuffle this YV into YU. This is nothing but just we need to compute the U basis, the result in another dimension. So when we stack the U basis in this way, and we can launch another NVM here, and then we get final result. So this is called the title rank matrix vector multiplication. It has three phases. The first phase is stack the V and multiply with the X. The second phase is it will do a shuffle. Third phase is it will multiply this U basis and with the intermediate result and get the final. So there is no approximation in title rank matrix NVM after we compressed it here. All the method in three phases is will give you same result if you just multiply one by one. Okay, so here is some numerical accuracy on the Mavis data set. It's a busy plot. You can see x-axis the error threshold. Basically, so you more restrict the error, more smaller error, then you will have less computational gains. So the color, the number in the tile is the speed up the theoretical flops compared to the original tile. And this is the tile size. And the straight hole ratio, it tells you what's the best. So given this setting and how much is your straight hole ratio. And then we don't want to lose too much numerical accuracy. So we set it at 95%. Like we only want 5% the performance numerical accuracy lost. And how many speed up can we get? So we can get around 3 to 4 speed up. So this is hardware and software specification. We deployed it on Intel, AMD, Fujitsu, NVIDIA, and NEC. Almost a lot of architecture. So they are very different. So for example, this is x86 and this is ARM and this is the vector engine, and we are using MPI plus OpenMP. And for the AI accelerators, we are relying on the Rock Plus and the Kublas. So this is high bandwidth memory, and for the EPIC, we have a very large level 3 cache, but it's this. But one more thing, it's not like we have a huge. The memory is called aggregated because they are like this They are distributed in the die. It's not a large block. It's just a several block and grouped together like this. Now let's see some results on synthetic data set. So on the left is a sustained bandwidth on synthetic data set. So bandwidth is higher the better. And we deployed on various vendor architecture, and you can see that we choose tile size to 100, 250, 500. and we want to get the best performance out of this configuration. And you can see that the ROM, AMD ROM, it has much better bandwidth compared to other architectures. And this is the case for the time to solution on synthetic dataset. And we reach below 200 milliseconds on ROM dataset. So next we compare the dense NVM via stylo-rank NVM. So this is the time breakdown on the synthetic dataset. And you can see compare to the dense NVM vendor library, we are almost a magnitude better than the than 2 magnitude better than the version. The major reason is that the Bliss AMD Bliss NVM and doesn't has good performance on the multi-thread version. Version. So yeah, this is the reason. And for the breakdown of the synthetic dataset, you can see most of the time is spending on the phase 1 and the phase 3. Okay, so this is the real dataset we tested using our astronomy dataset. Again, we present the sustained bandwidth and time to solution. You can see ROM performed the best, and also from the time to solution, ROM is the best. Next, we show the roofline performance model of EPIC ROM. We are go beyond the DRAM memory bandwidth. Actually, we are hitting the L3 cache bandwidth. So this is the bandwidth and the jitter on various dataset because, as I said before, we require a very tight, very stable time to solution. However, the ROM get the best time to solution, but it is not the best stable one, the most stable one. So Aurora is the most stable one. It is very concentrated to a certain time to solution. So in this section, we using stylo-rank NVM to accelerate the hardware real-time controller of the AO system. We from the application, we measure what the accuracy the application need, and from the architecture level, we deployed on almost all of architecture and find the best architecture for this errors. Next application is seismic redatuming by inversion using Marchenko-based method. It's batched TRMVM. Okay, so next application is seismology. It calls seismic redatuming by inversion using Marchenko-based method. I will mainly introduce algorithm batch TRMVM and mixed precision TRMVM. So you can see it's just another 2 variants of the TRMVM, but the application is different, so the data is different, and but the logic is the same. You have your data matrix, and then you measure the accuracy, measure the error that you need to get from the application, and then you use stylo-rank for the approximation, and you want to extract the best performance using the algorithm and using the specific hardware. Okay, so let's have just a simple introduction to the seismic imaging. So what is seismic imaging? Basically, it wants to know the what's going on beneath the in the underground. So for example, carbon dioxide sequestration, and we need to measure whether the carbon dioxide is leaking if we put this gas in the underground. And this is what you get using a seismic imaging method. So this red star and blue triangle is the source and the receivers. So if you want to get the image like this, you need to put a source this red star here, and then you can put the receiver. The source is just the signal. You send a wave signal like an air gun in the sea level. Then you generate the wave. The receiver is the signals that you can receive the signals. So the Marchenko data mean and the great innovation is that it does not require to put the source and the receivers on the boundary of the we call it area of interest, like this one. You just need to put the signals the source in the sea level, and then it get the data at this also at the sea level, but somehow it can, like you put a virtual source in the receivers here. So this is the formula. I won't go into the detail of this. I just want to let you know they want to solve actually an inverse problem. So these are all the data. These are also the data, and this is unknown. So the multi-dimension convolution operator, it's nothing but just you transfer your data from the time domain to the Fourier domain, and then do the convolution or multiplication in the Fourier domain, and then convert it back to the time domain. So this R operator, yeah, it's just a real, and then internally it has in the Fourier domain, it has a batch matrix vector multiplication, and this is the most time-consuming part in this application. We want to further optimize this operation kernel. So here's a basic introduction to the experiment setting, and the source and the receivers are 10K by 10K, so which means that our matrix is 10K by 10K. We call it the frequency matrix. Once you convert the time data to the Fourier domain, you have Fourier frequency matrix on each frequency. So for each frequency, we need to do the matrix vector multiplication. Yeah, and this the visualization of the frequency matrix, and you can see it is clearly has a banded structure, but you cannot, but it is dense. It is dense. From our experience, if you remove the off-diagonal part, you cannot fit the accuracy. But somehow you need to use low ranks technique to had better approximation of the matrix. So again, we do the rank analysis that we found that almost all the tiles is low rank. And then this is interesting because the frequency, we have 150 frequency here. And this is the rank summation in the frequency matrix. You can see with the frequency goes up, then it tells you that the information in this matrix is not cannot be compressed compared to the low frequency. This is it is reasonable because the high frequency information is hard to compress. So this is a load balancing optimization of the what we proposed about the batched TRNVM. We just first do phase one of all, and then do phase two of all, and then do phase three. It's just like you remove the synchronization, and then we also use dynamic scheduling for the intranode load balancing. And this is because we are doing on the vector engine, NEC vector engine. So this is called VE. If you have 8 VE, then we might do think about how to balance the workload between the vector engine. It seems that like a simple reshuffle of the reorganized of your data on each node, like we call the zigzag. Just originally, because the workload is increasing with the frequency ID or the high frequency cannot be compressed, and then you just need to first put the forward and then backward put and then forward put it. We call the zigzag mapping, then you can achieve relatively flat flops allocation. Okay, so this figure is just to tell you um, how better what it would be if you use our low rank approximation. And this is just actually I this is for the seismic scientist to read, but you can think that with the error threshold goes up, for example, go to 10 to the power minus 2, then you can see a lot of errors here. But if you using the 10 to the power minus 1, 3, then you can almost there's no error here. So we do the experiment on two architecture, Intel Ice Lake, so it's x86 platform, and then the NEC vector engine platform. So we do, again, we use dense NVM as benchmark, and we first run each frequency one by one, and then you can see that because the flops of in the higher frequency it will be larger, so the time will be larger. But for the load balance, if you look at the bandwidth, you see actually we are higher than it is interesting that when we deployed on the Intel Cascade Lake architecture, the lower frequency is actually beyond the DRAM cache. It is because the data is so small that it can fit inside the L3 cache. But when the data is too large, then you have to go to the DRAM memory. Then you are bounded by the DRAM bandwidth. Okay, so this is just a flops count for the 8-vector engine to prove that our previous mentioned the remove the synchronization and the make zigzag mapping strategy from the first. You can see they are not evenly distributed, and even the threads within one vector engine is also not even. So with the dynamic scheduling and the remove the synchronization, you can achieve the in-node intra-node balance, and then using the zigzag mapping to achieve the internode. So finally, this is the final performance that we allocate the flops to every threads evenly. So this is the performance comparison on Intel the NIC platform, and you can see we on the vector engine we are much better than Intel because we are using high bandwidth memory. You can see here we are very close to the high bandwidth memory peak. So this is the scalability result, and you can see with when I increase the number of VEs. So this is the linear scalability, and we using our final implementation can reach more than 100 terabytes per second in in the vector engine. On 100, I think it's 128 vector. Yeah, here then just zoom in, and then it is just the performance comparison of on other Intel Cascade Lake platform. Well, finally, we are 2 magnitude faster than the dense NVM implementation. So here is introduce the TRMVM on GraphCore. Just to we want to answer will HPC application benefit from AI accelerators? Yeah, the answer is yes. So the GraphCore is called Bow IPU. So it's IPU. It's a intelligent processor unit, and we using a seismic redatuming data set, and you can see this is the per frequency result, and we are the best among the all other architecture. This is bandwidth, and for a single memory bound kernel will reach 1 terabytes per second. And also for the Cerebus system, this is from our latest Golden Bell finalist papers result, and we deployed the TRVM on the Cerebus platform. So here we on the 6th Cerebus CS2, which is the minimum hardware requirement for the TRVM for seismic data set, we reached more than 11 petabytes. And then we scale on the 48 Cerebus CS2 node, we get more than 86 petabytes per second. So this number is very large, and it's almost hit the memory bound of the largest supercomputer on in the world. Yeah, so this section we designed a batch TRVM, and then we have some further optimization, and then we deployed on the NIC, all the hardware AI accelerators, and then we achieve a good performance. Okay, so last I would like to introduce the mixed precision batch TRVM on NVIDIA GPU, because there's we can do low rank, and then we can also do the mixed precision. So is it possible that we can bridge two together to find the best one? So it's we try to use distance aware measure. So this is another branch of method called distance aware matrix routing. I'll introduce later. And then we explore GPU implementation, and we're leveraging the FP16 and Int8. So the original source and receiver matrix is like this one, but this is because how we arrange the data. If we arrange the data in another gathered signals that is gathered together, it means that, because let me explain in this way. So if I hit this is the source, and now here the receivers is arranged in a line. So which means that the first block, then you put the first line in the first block, and then in the second line you put them in the second block. However, it is not, they are not close to each other. You mean, so for example, the first line, this one and this one, they are very close, but in the matrix they are very far from each other. So what we want to do is that we want to gather them together. So why we want to gather them together? Because once we gather them together, you can see the information is more concentrated. So the information is once the information is more concentrated, then you can get a higher compression rate. So here you can see that without the normal ordering, it's just the normal data set. We can using the same accuracy, we can get 30 gigabytes compression. However, if we call it in the Hilbert space, then we can get only 6 gigabytes. So it's a huge data set reduction. So once we reduce the data set, then we can run faster, and we can do more operation. So okay, so now we want to introduce the implementation of TRVM on the GPU. Basically, we rely, if you remember, we have 3 phases, and then for each phase 1, we have multiple NVM. We use CodaGraph, and for each NVM, we assign a stream on it, and then synchronization, and then for the phase 3, again using multiple stream. So for the other optimization related to the memory, coalesce the memory access is vectorize the memory access. Yeah, we both further optimize this one. And also, I want to introduce that we also extend the int8 expression. So we first convert this float number to the int8, because when we use the int32 integer accumulator, so we will be faster than the FP32 or FP16 accumulator. So, but it's kind of it's a bit complicated. So you need to convert your data into int8 and then use int 32 accumulator and then convert it to the FP16. This is because you need to shuffle the data. So it's some internal process. We need to convert it back to the FP16 and then we reshuffle and then we downscale again. And then we, again, we convert the input U data and RYU to the int 8 and then use int to accumulate. And finally, we get the FP32 result. So this is a complicated figure, but it tells you the dense NVM we have. So this is SNR. It's like we are using straight hole ratio in astronomy, but we are using as a signal noise ratio in the seismic. So the signal noise ratio is the higher the better. And this is banded. It's an idea that if we only keep the yeah, so this is a combination. For example, if the off diagonal part we use FP32, or maybe off diagonal part we just zero it, or we use a lower precision. So it means that in a single matrix, you have two different precision. Here you can see our method is that we use a pure mixed precision int8 here, and our dataset size is only 2 gigabytes. So finally, because we can reduce because we convert from FP32 to the int8, that 4 times reduction. Yeah, it's tell you that we use a very limited dataset size to reach a very high signal noise ratio. Then here are some experimental result. So this is a bandwidth, like we use multiple CUDA streams to add the parallelism. And also in the middle, the number of CUDA stream increase, then the bandwidth will be increasing. We are reporting mixed precision FP16, and also binary float FP16. This is the data type that in the NVIDIA GPU. And so you can see that mixed precision int8 is actually faster than FP16 variants. Here that we show the TRNVM result that we break down, this is dense NVM, and then this is FP32, this is FP16, BF16 int8. Finally, we can get more than 1 magnitude performance improvement compared to the dense one. And even compared to the FP32 TRNVM, we have a significant improvement. So finally, the data set, we go from the 120 gigabytes to only 1 gigabyte. We remove also more than 2 magnitude. And this is the scalability result to show that we have a decent scalability. So compared with other architecture, what we did in previous one, we Intel Ice Lake AMD ROM, Fujitsu, Nicorora, and the A100. So we are finally the best variance is mixed precision data with Hilbert ordering. Okay, so here we explored the mixed precision and we evaluating the numerical accuracy and the trade-off of the mixed precision TRVM. We also proposed the distance-aware matrix reordering method, and we also use CUDA-Graph API. Okay, so these are some publication related. So if you are interested, so yeah, these are the softwares for this talk. If you are interested, please go to the GitHub and have a look. I'm very happy to further discuss the detail with you.